Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Differential Equations series and concerns basics of differential equations. This guide explains what a differential equation is and also describes the language used to categorise them. It also discusses the different kind of solutions to differential equations that you may come across. Introduction. It is very common, especially in science, for a relationship you are considering to involve a derivative of some kind. The study guide, What is Differentiation, explains that a derivative is rate of change of one variable with respect to another. For example, in physics, acceleration is the rate of change of velocity with respect to time. As a result of this, equations and relationships in science are often described by differential equations, or simply DEs. For example, rate kinetics, dc by dt equals kc. Acceleration, a equals d2x by dt squared. In the first equation, the rate of change of the concentration c with respect to time depends on c itself multiplied by a constant k. In the second equation, the acceleration a equals the second derivative of the position x with respect to t. A differential equation is a mathematical relationship between functions and their derivatives. The derivatives found in differential equations can be written in many different forms. The Leibniz form, dy by dx, d2y over dx squared, and so on. The Lagrange form, y prime, y double prime, and so on. The Newtonian form, x dot, x double dot, and so on. Time derivatives only. This study guide will help you identify the different types of DEs you may come across. To solve a differential equation, you need to find a function which fulfills the constraints of the equation. For example, in the rate kinetics equation above, the concentration C is described by a function whose derivative is equal to C itself multiplied by k. You can work out the nature of the functions involved in differential equations in many ways, and as DEs contain derivatives, it makes sense that their study follows on from basic calculus. It is very useful for you to have a good grasp of the language of, and methods involved in, differentiation and integration before beginning to study, and more importantly attempting to solve, DEs. You can explore the range of resources, steps into calculus, which can help improve your basic calculus if necessary. Classification of differential equations. Mathematicians are fond of categorising things, and differential equations are no exception. In the rest of this guide, you can assume that the function under scrutiny is y, and y itself is a function of a variable x. In the acceleration equation on page 1, the function of interest is the position, and the position itself is a function of time. Differential equations can be one of two fundamental types, either linear or non-linear. A linear DE, the function of y and any of its derivatives, can only be multiplied by a constant or a function of x. In a non-linear DE, more complicated functions of y and its derivatives appear, as well as multiplication by a constant or a function of x. As well as being linear or non-linear, a differential equation is also characterised by the type of derivative it contains. Ordinary differential equation, ODE, contains only ordinary derivatives. Partial differential equation, PDE, contains partial derivatives. Some of the most famous and important differential equations are PDEs. The order of the differential equation is given by the highest order derivative in the equation. For example, the most common orders are first order DE, the highest order derivative is dy by dx, or y prime, or x dot. Second order DE, highest order derivative is d2y over dx squared, or y double prime, or x double dot. The order of the derivative in Lagrange notation is the number of primes, or dashes next to a variable, and in Newtonian notation is the number of dots above a variable. Example: classify the following differential equations. 1. Y double prime plus 3y prime plus 2y equals 0. This is a linear second order ODE. Linear, as y and its derivatives are only multiplied by constants. Second order due to the second derivative y double prime. And ordinary, as only ordinary derivatives are present. 2. dy by dx all squared plus e to the x multiplied by y equals 0. Non-linear first order ODE. Non-linear due to the squaring of the y prime term. First order due to the first derivative y prime. And ordinary as only ordinary derivatives are present. Here it is worth noting that d by dx of dy by dx equals d2y over dx squared, the second derivative of y with respect to x. This does not equal dy by dx all squared, which does equal dy by dx multiplied by dy by dx. So y double prime in 1 and dy by dx all squared in 2 are not the same. 3. dy by dx plus cos y equals 0. Non-linear first order ODE. Non-linear due to the cos y term. First order due to dy by dx. And ordinary as only ordinary derivatives are present. 4. X multiplied by y double prime minus cos x multiplied by y prime plus 2x equals 0. Linear second order ODE. Linear DE, as y and its derivatives are only multiplied by functions of x, even though these functions are non-linear. It is the functions of y which control the linear/non-linear nature of the DE. Second order due to y double prime, and ordinary as only ordinary derivatives are present. 5. d3y over dx cubed plus 3 dy by dx plus y equals 0. Linear third order ODE. Linear because y and its derivatives are only multiplied by constants. Third order due to the third derivative d3y over dx cubed. And ordinary as only ordinary derivatives are present. 6. Y double prime cubed plus 3y equals sin x. Non-linear second order ODE. Non-linear because y double prime is cubed. Second order due to the second derivative y double prime. And ordinary as only ordinary derivatives are present. 7. Partial u with respect to partial t plus k squared partial 2u with respect to partial x squared, k is a constant. Linear second order PDE. This is the famous one-dimensional heat equation, which is linear because the derivatives are only multiplied by constants, partial as partial derivatives are present, and second order due to the second order partial derivative of u with respect to x. Solving differential equations. Some of the greatest mathematicians who ever lived have devised methods to solve specific types of differential equations, and often you will see equations which are named after the person who solved them. 1 minus x squared multiplied by d2y over dx squared plus 2x multiplied by dy by dx plus n multiplied by n plus 1 multiplied by y equals 0. This is Legendre's equation. It is a second order linear ODE, common in problems with spherical symmetry. X squared multiplied by d2y over dx squared plus x multiplied by dy by dx plus x squared minus n squared all multiplied by y equals 0. This is Bessel's equation. It's a second order linear ODE, common in problems with cylindrical symmetry. The second partial derivative of u with respect to x plus the second partial derivative of u with respect to y plus the second partial derivative of u with respect to z equals 0. This is the three-dimensional Laplace equation. It's a second order linear PDE common across various disciplines in physics. There are hundreds more whose solutions require knowledge of a wide range of brilliant techniques. You can greatly improve your mathematical skill by reading about how various differential equations were solved. There are many differential equations which can be solved by mathematical methods to give an exact function which satisfies the dE, and these tend to be those which fit a specific form or pattern. See study guides, separable differential equations, linear first order differential equations, homogeneous differential equations, and second order differential equations. If a dE can be solved to give an explicit or implicit function, then the solution is said to be analytical. Many different types of differential equations cannot be solved by mathematical means to give an analytical solution. Commonly, computer models are used to find out how these kinds of dEs behave. For example, weather forecasts are determined this way. Such solutions are not really solutions at all, but approximations to the exact solution. However, these approximations are often referred to as numerical solutions, as numbers are inputted directly into the differential equation to determine the output. Solving differential equations. General solutions. Solving a differential equation finds functions which satisfy the conditions described by the dE. For example, the linear second order differential equation y double prime plus 3y prime plus 2y equals 0 describes a function y where the sum of its second derivative y double prime plus 3 times its first derivative 3y prime plus twice itself 2y is equal to 0. Solving this ODE means the same as finding any functions which satisfy this relationship. Example. Show that both y equals e to the minus 2x and y equals e to the minus x satisfy y double prime plus 3y prime plus 2y equals 0. Begin by differentiating. If y equals e to the minus 2x, y prime equals minus 2 e to the minus 2x, and y double prime equals 4 e to the minus 2x. Then substitute these results into your differential equation. Y double prime plus 3y prime plus 2y equals 0 becomes 4 e to the minus 2x minus 6 e to the minus 2x plus 2 e to the minus 2x equals 0, which is true. So, y equals e to the minus 2x is a function which solves this ODE. Now look at the function y equals e to the minus x. Again, begin by differentiating. Y equals e to the minus x, y prime equals minus e to the minus x, and y double prime equals e to the minus x. Then substitute these new results into your differential equation. Y double prime plus 3y prime plus 2y equals 0 becomes e to the minus x minus 3 e to the minus x plus 2 e to the minus x equals 0, which is again true. So y equals e to the minus x is also a function which solves this ODE. You can also multiply either of these functions by a constant and still get a solution to the ODE. It seems like you have solutions which look like either y equals a multiplied by e to the minus 2x or y equals b multiplied by e to the x, where a and b are constants. See the discussion below. Both of these solutions give 0 when substituted into the ODE, and so you can add them together and still get a solution, as 0 plus 0 is 0. So the solution looks like y equals a multiplied by e to the minus 2x plus b multiplied by e to the x. This is a general solution of y double prime plus 3y prime plus 2y equals 0. All methods of solving DEs introduce unknown constants, usually simply called constants, and they often appear as letters in alphabetical order. There are various ways constants are introduced into DEs. For example, as integration is the inverse of differentiation, you would correctly expect that indefinite integration is often used to find the solution of a DE. Using indefinite integration introduces a constant into your answer as plus c. Solutions to DEs which contain unknown constants or coefficients, such as the one above, are called general solutions. The number of different unknown constants in a general solution of a differential equation is equal to the order of that differential equation. Solving differential equations, particular solutions, using initial conditions and boundary conditions. If more is known about the situation that a differential equation describes, you may have extra information available which enables you to calculate the constants in your general solution. These conditions are called initial or boundary conditions and are given as mathematical statements relating to the DE you are solving. Using boundary conditions is covered in depth in the study guides for specific types of differential equations. See Steps into Differential Equations for more details. However, an example of boundary conditions for y double prime plus 3y prime plus 2y equals 0 may be y of 0 equals 1, which tells you that when x equals 0, y equals 1, y prime of 0 equals 1, which tells you that when x equals 0, y prime equals 1. You can substitute these into the general solution to get simultaneous equations which imply that a equals minus 2 and b equals 3. When you have found any constants, you substitute them into the general solution of your DE. You should now have a solution which does not contain unknown constants, and this is called a particular solution. And so, y equals minus 2e to the minus 2x plus 3e to the minus x is the particular solution of y double prime plus 3y prime plus 2y equals 0 for y of 0 equals 1, y prime of 0 equals 1. Further guidance and information. If you have any further questions about this topic or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. Telephone 01603 592761. Email dos.help@uea.ac.uk, or you can visit our website www.uea.ac.uk/dos/let. There are further resources on many other aspects of mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills.